All right, so this is my way of doing the AP quiz number 3. This is number 1 from the year 2006. First of all, for drawing the free body diagrams for this situation, you have the block over here that has the normal force acting up on the block. You have the force of kinetic friction acting toward the left as it's sliding. And you have the force of, and we've got the force of gravity acting down, which is equal to the block mass, the mass of the block times g. And by the way, this force acting downward is felt as a normal force acting on this slab over here. I'll call it n prime. And it's going to be equal in magnitude to this force of gravity acting on the block. That's what the slab is feeling as that block is pushing down. So I'm going to call that mass of block times g. And that's all for the block as far as the forces. Over on the slab, you have that normal force, or that weight of the block, if you want to think of it that way, pushing down on it. You also have its own weight, so the force of gravity on the slab. And then you also have force of kinetic friction. This force of kinetic friction is pushing in this direction, and it's going to cause the slab to move. And then you have the normal force of the table, or whatever it is underneath the slab, pushing up. And those are the force diagrams. For part B, calculate the velocity final. The way that I did this was to use conservation of momentum. And so that's the way I'm going to do it here. So for this, we have just momentum initial equals momentum final. And momentum initial, well, you have the mass of the block times the initial velocity of the block plus the mass of the slab times the initial velocity of the slab. And that all equals 0 because the slab initially is not moving. And then in the end, the slab and the block are moving together, so I can count them as one object, the mass of the block plus the mass of the slab times whatever their final velocity is. So once you plug in these values, because you know everything, you have one equation, one unknown, you can solve for velocity final and get 0.57 meters per second there. Okay, so what I did is I just squished down part B over here so it doesn't take up so much space. So here's part B. And now for part C, it asks us to calculate the distance the slab has traveled at the moment it reaches velocity final, or that 0.57 meters per second. And so really I'm looking for a delta x. And so I'm going to be using a kinematic equation for this. And this is all for the slab. Velocity final for the slab squared equals velocity initial for the slab squared plus 2 acceleration of the slab times delta x. And it's acceleration in the x direction. Again, all of this for the slab. Initial velocity was 0, so that takes care of that. And so in the end, I'm going to get delta x to equal whatever our final velocity is squared divided by 2 times acceleration. Well, we know what the final velocity is because that's what we had solved for up here. We know what 2 is, it's 2. And so what we need to know is we need to know how is that slab accelerating? And so that's the big thing here, is to find how much that slab is accelerating and then putting that in there. So in order to do that, I need to use a free body diagram, or look at the free body diagram for the slab and look at what are the forces in the direction of motion. Well, the only force in the direction of motion is this force of kinetic friction. And so if I do a Newton's second law for the slab, I get the net force on the slab in the x direction equals the mass of the slab times the acceleration of the slab. And by the way, this acceleration of the slab here is going to be very useful because that's going to come in down there. So that's what I need to solve for. So what do I have for my net force? Well, I have only one force, and that's the force of kinetic friction. Force of kinetic friction equals the mass of the slab times the acceleration of the slab. Well, what does the force of kinetic friction equal? It equals mu sub k times the normal force. Well, which normal force are we talking about here? Well, we're going to be talking about the normal force that's part of the interface between the block over here and the slab over here. And so that particular normal force is going to be the one that's here, and that's the same Newton's third law normal force to this one down here. So in both cases, they're equal in magnitude to the mass of the block times the acceleration due to gravity. So I'm going to rewrite this as mu sub k, and the normal force, again, mass of the block times g, and all of this equals the mass of the slab times the acceleration of the slab. Okay, so we're going to solve for the acceleration of the slab now. Acceleration of the slab equals mu sub k times mass of the block times g divided by mass of the slab. We know all these values. Mu sub k, it tells us in the problem, is 0.2. Mass of the block we know, 9.8 meters per second squared for gravity, and the mass of the slab we also know. And so we can solve for that. And when we do, we get an acceleration equal to 0.33 meters per second squared. And now that I know this, I can plug this in for my acceleration in the kinematic equation and get for my delta x then for the slab to equal 0.49, I think is what the final answer comes to, meters. So that's the answer to part C. For the last part, part D, you're asked to find let's see here, calculate the work done by friction on the slab from the beginning of its motion until it reaches velocity final. Well, since friction, and remember here, friction is what's causing the slab to start to move. Okay, a lot of people always think that friction slows things down, but it's kinetic friction in this case that's causing this slab to start to move to the right. And so when we look at the slab, force of kinetic friction is the only force acting in the direction of motion, and so that's doing all of the work. And so I can either multiply the force times the distance that it traveled, that displacement, or I can do the work kinetic energy theorem that the work equals the change in kinetic energy. That's the one I'm going to do here. So work done by friction equals kinetic energy final, subtract kinetic energy initial, but it started off at rest, so kinetic energy initial is 0, and kinetic energy final then is going to be what the work is equal to, kinetic energy final of the slab. So that's 1/2 mass of the slab times the final velocity of the slab squared. And so putting those values in will give us work to equal 0.49 joules. And that is the answer to part D. So again, the 1/2 times the mass of the slab times that final velocity, which is not that, the final velocity, which we determined way up in part A, which was the 0.57 meters per second. And then that quantity squared. All right, so hope this helps. Make sure that if you still have questions on this, to please ask.